he has mouse.
All right.
Yeah, it shifts.
It's just,
So,
it could be better.
so
He
I have
needs the link
I have this
for it.
feeling of fear, and I don't know what I did, other than perhaps I had a moment of dyslexic ideas.
Yeah.
Okay. So, hey. So on page
What up, little
34,
big dog?
this would be a good refer to page if you forget stuff like this guy does. And down in the bold it says the
Hi.
further
Come to class.
our sample
Because you called me.
is from the mean,
Okay, whatever, bye.
the stronger
Oh.
our evidence is against the null.
Oh, sweet. Alright, well that's good.
And I have this
Yeah,
feeling that I
okay.
flipped it over in my head, and I don't know why I did. But I don't know if I flipped it over in my head. But like I had this. There's times I dream about school, and I don't know why I dream about school. But I had this notion that I flipped this over sometime this week, and I didn't mean to. So where you need to think about this is when that p-value is less than 0.05 on a one-tail,
Can I get a ride home for
or the p-value is less than 0.10 on a two-tail,
KB dipped on me?
meaning like if I have a really small value way out here or way out here or both, that's where we reject our null. And I feel like I flipped that over, and I'm so sorry. But if I didn't flip it over, then just go with it. Okay, so I just wanted to talk about that
Wait,
brief.
so P is less than 0.05.
Yeah, did I flip that over?
I told you.
Did I flip that over?
Yeah, you did.
I did, okay.
'Cause I told, when I said P is greater than, you failed to reject it.
Right, when p is greater than 0.05, fail to reject. When
Yeah,
it's
see,
less than 0.05,
You
reject.
switched it earlier.
So I did flip it over.
'Cause earlier this
If
week-
it's less than 05, you reject.
Reject.
Told you.
Like I totally flipped that over in my head.
Listen, when we did that one question on Tuesday, the P was greater than 0.05, and he said reject and all, not failed to reject. So I was right the first time you were wrong.
So,
Remember our point, our.
Would you send me?
We saw that.
Hell yeah.
so I'm sorry,
You flipped it.
we flipped it. At least there was no points that anyone lost on it. So I just want to make sure, like,
Got
maybe at the top of page 34, put like a big star so you can go and find that bold printed thing to make sure that we get it. I'm so sorry. I feel silly. But hope y'all forgive me. I hope I haven't destroyed your world of statistics. All right, now I'm going to be on page 111. So if you want the points, get it out, fill it out. It'll totally help you on the test we have next week. So again, next week when we do have the test, there's many different versions. But
Did you remember that?
somebody in the class would probably share your exact page 1. Somebody different in the class would probably share your page 2. Somebody different in the class would probably share your page 3. Someone in the class would probably share your page 4. So you guys get to work on it together, but it's a matter of, you know, like, oh, okay, I can't work with this person anymore because my questions don't match their questions. So just kind of figure that out. I don't know, trying something.
Is that the same chain?
All right, so page 111. Here we go.
This is chain?
All right. Says the local newspaper claims that the average home price in Denver is $400,000. Researchers select 400 random homes sales to test this theory.
It's the same
400
chain.
randoms.
That's him, bro.
Homes had a sale price of $378, standard deviation of 45,000. Is there stronger is there evidence that the average home price is different than 400,000? Okay, so they're using the word different, so one or two tail. This is a two-tail event, okay? Which means on our little distribution, we're looking at the two ends. They're symmetric, but we find, usually we'll find one side, then we just can easily find the other side. Alright, so, let's see how we can walk through this. Switch sides with coffee. Alright, so this is problem number one. We have a null, we have an
Let me
alternative.
see.
Alright, so homes are equal to 400,000. And then homes are not equal to 400,000. There's your definite two-tail right there. We don't have a direction. Okay? So, check for any red flags or assumptions. I don't think we have any red flags. We have a large sample, and it was randomly chosen, and we're just taking it from the same area. They're talking about Denver. Their sample, random sample, was from Denver, so I think we're okay in all that. I don't think there's a red flag that we have to worry about. But then when we create our normal curve or our normal distribution on this, we do need to find our standard error. And if we recall, our standard error will be the standard deviation divided by the square root of our sample. So our standard error in this case is going to be 2250 if we work this out. 45,000 divided by square root 400, or 45,000 divided by 20. And then we can base it on here, so we can say 400,000, then 40250, 40450. Sorry, and then go out one more. And the last one is 406. 750. All right, and then going the other way, 397, 750. Go this way a little bit more, 395, 500. And last one is 33. I think that's right. Okay. So, once we have that, we need to take a look at our p-value. Now, because it's a two-tailed test, we want this to be less than 0.10, because we double 0.05. Double 0.05 becomes 0.10, right? So 0.05 plus 0.05, or 0.05 times 2. Because it's two-tailed, this is what we're looking at. Alright, so now I can jump on to Desmos.
Oh, shit. Fuck. Hey, mark him tardy so he doesn't get perfect.
You will.
Oh, yeah.
He's getting a UP. 22 minutes late.
Really?
Unexcused present.
Ooh. I heard his ass. Where's he at?
Yeah, I don't know. Alright, so normal distribution. Normal distribution, we have the 400, comma, and then our standard error was 225, 50. So there's our normal distribution, and this is only going to find us one way, which is fine. Hello? Hello? We're on page 111. Then we have 378. So we can go one way or the other. Actually, I'm going to go. They're claiming it's 378, so we're going to go down this way. So that is pretty small. If I take that and I double it, if we double it, we come up with roughly 1.4 times 10 to the negative 22nd. So p-value is 1.4 times 10 to the negative 22nd. That is definitely less than 0.10. So if we go to that, the farther our sample is from the mean, the stronger our evidence against the null. So we reject the null. So in this case, we reject our null. Okay? Reject the null. We found strong evidence. We found strong evidence against H0. That's sure. Alright. So, explain why this is two-tail. What word in the problem tells you this? We talk about different. We have the no equal, not equal to of our alternative, things like that. Which type of error is plausible? Explain which type of error makes the most context. So I would think a type 1 error would take place. So we found strong evidence that the home sale price is different than $400,000 when it really isn't. Okay? Because we found evidence against null when null is true.
Help him get away.
Okay? But I would say you came up with some unbelievable evidence, especially that you had sampled 400 random homes in Denver to find that. Of course, these numbers are probably many years ago. Alright. Then, next page 112 says, the average length of a jury trial in Colorado is known to be 440 minutes. The state of Colorado changes the law on jury trials. Will these changes affect the average length of time? So the first 100 trials are used in the study. This, whether this new law will have an effect on the average jury time. The average of these 100 trials is 426 minutes with a standard deviation of 64. Okay, I already see some red flags here. Okay. So, if we were to establish our null, we would say that trials are equal to 420 minutes. Our alternative is that our trials are not equal to 420 minutes. Okay? So they're saying that it affects it. That's not a direction, so this is a two-tail situation. Agree? Yeah.
Wouldn't it be reversed though? Because if the alternative is the one you're actually testing, and you're testing will the changes affect the average length of time?
Ooh, I like this. Okay, so if I turn to my alternative to it's equal to 420 minutes, that doesn't allow us to do a two-tail test.
Okay.
There's not a direction on equal to.
Okay.
It's like you're exact.
Right, yeah, okay.
Does that make sense?
Yeah.
I mean, that's the best I can come up with on it, but that's a great question. So
Okay.
I like that. I like
Thank
that
you.
thinking. What else do we know here? Show it better on the screen. All right, then it says check for any red flags. So red flags in this, they took the first 100 after this. So it was not random. Okay, they just said, hey, we had a great sample size of 100, but I just took the first 100 cases after to see if this actually worked. So it's not random, it's just by chance. So that's kind of a red flag, so keep that in mind. If we do our normal distribution, we have 420 minutes here. We need to figure out our standard error. Our standard error, we knew that the standard deviation was 64. We know that the sample size was 100. So that's 6.4. So that's going to go to 426. 0.4, that's gonna go to 432.8, and that's gonna go to 439.2. And subtract it, we're gonna go to 413.6, 407.2, and 400.8. Alright, and then they said, what? Oh, we were at 436 minutes. Oh, wait. 436 minutes, which is over here. So 436, so that's 16 above, so I'll go 16 below as well. 16 below will take us down to like 404.
That's fake. That's gotta be fake.
Okay? So there's our two tails. Because we're at two tail, I'm looking less than 0.10 versus 0.05 because it's two tail, I need to double it. Okay? So let's take a look. Jump on to Desmos. So we're going 420 in the middle. We're going standard error 6.4. Doing this. And then we are looking at the 436 minutes or greater. Alright, so we get 0.062. If I take 0.0062 and I multiply it times 2, I get 0.0124. So our p-value is 0.0124. Is that value less than 0.10? The answer is yes. This is less than 0.10. So we what? Reject the null. We reject the null. Strong evidence against. I gotta learn how to space my stuff better. Alright, using an alpha of 0.05, explain. Okay, so now this alpha, where it pops in, if I have an alpha of 0.05, remember we make up our alpha value. We don't know. It goes along with our confidence interval. It could say that we are 95% confident if we did this again, where our results would have the same chance of happening. So that's where the 0.05 comes from. So, bless you. So we reject the null. So this means that we have, this basically means we have a 5% chance of a type 1 error. That's basically what it comes down to. The conclusion I came up with last year was we reject the null, we find strong evidence that our new law is changing the average time of the trial. Okay? In this case, it looks like they made it longer. Explain why this is two-tail. We are investigating a change to trial time, not a direction. We're not saying they made it less or more. And which type of error is plausible? This is a type 1 error. It's pretty hard to get a type 2 error. We find strong evidence to change the trial when the new law has no change. So we change trial length when it is the same. Okay. Woo! Good, good, good. Everyone good with this? Feel happy? Alright. Today is going to be 610. I'll be on page 41. So page 41 is where we're doing the math here. Alright. So we're good with the standard error, for the most part, being the standard deviation over the sample size. Okay, we've worked with that quite a bit. So we're gonna look at something called a t-distribution. We've talked about this before. T-distribution is gonna deal with degrees of freedom. Okay, now you're gonna use a t-distribution. When we're gonna use a t-distribution when the sample standard deviation is given, not the population standard deviation. Okay? Alright, so if we were dealing with one mean t-test, degrees of freedom, simply one less than the sample size, the t-distribution changes somewhat, different degrees of freedom. Second page shows you a t-distribution. T-distribution looks very much like a normal distribution. It does go around 0. Okay, the higher your degrees of freedom, the skinnier or the steeper that it gets, the lower, the fatter your graph gets. So if we were to look at this example, it says what percentage of the t-distribution with 27 degrees of freedom is greater than the 2.3 standard deviations above the mean. So all we would do on Desmos in this case, get rid of this, go to t-distribution where we can find it. T-distribution, degrees of freedom. They said 27 degrees of freedom. You hit your graph. Again, it looks like a normal curve, which is what we want. I like purple. And then if they said greater than the mean, so we're going to go 2.3 or greater. We're talking about that little tiny purple shaded region down there. So in this case, we come up with the 0.0147, or we can multiply by 100 to make it 1.47%. What percentage of t-distribution with 16 degrees freedom is between 1.5 standard deviations? So if I do a t-distribution here, just on top of it, t-distribution of 16 degrees of freedom. Okay, it's really close to laying on top. It's close enough to 27. It should look fairly similar. Is between 1.5 and 2.5.
That was fucking funny.
So I take that graph away. So it's that little tiny shaded region. So in this case,
Wait, but why is it on like the 42, why is it on the negative 1.5?
oh, it should have been a negative. It said below 1.5. There it is. Is that right?
91.
Yeah, so it comes up to 91.2% roughly.
Yeah.
Yeah. Of course, if I read, I'd be better. So you'll see that the t-distribution uses the z-scores. The z-scores are based on, because it's revolving between 0 and out, in my case, out to 4 in each direction. Okay, so there's a z-score that does taking place there. So the nice thing is, because we're using Desmos, Desmos does it nicely. If we did not have Desmos and we were using the graphing calculator, it's a much longer process to do this. But fortunately, our knowledge of Desmos is doing it all correctly. My answers are matching what they have in the book, which is a happy day. All right, so 6:10 homework. So Monday, we'll take a good, honest look at page 113 and 114. And just know, Thursday next week, we have our chapter 6 test. And again, you get to do it together. It's a front, back, front, back. In this class, there'll probably only be 2 or 3 tests that would be truly identical, but your front page would probably match 4 other people's front page, or 5 other people's. Your second page would do the same, your third page would do the same, your fourth page would do the same. So you get to work on it together, but you might not be able to pair with your exact groups you've been working with. You kind of have to, make this work, which is fine. It's great. I love it. And it's not that long of a test. The first 2 pages, the front back, are multiple choice. And then the last 2 pages are this type of problem. So you just have to go through it. Cool? Everyone's happy? No one's sad this day? All right. I'm done recording.